Okay, so good afternoon. On behalf of IASTA, I welcome all who have joined us for attending 22nd lecture of IASTA monthly online lecture series. I am Manish Joshi, Secretary, Indian Aerosol Science and Technology Association. IASTA was formed in 1988 and the current executive committee serves under the leadership of Professor Sachidanand Tripathi, IIT Kanpur. IASTA conducts conferences, schools, and lectures, and by doing so, it promotes exchange of knowledge pertaining to aerosol science and its applications. This is 22nd lecture in an important series of events from IASTA, and we will be hearing Dr. Pandithurai from IITM Pune today. He is not only a renowned name in aerosol research, but also a part of current executive committee of IASTA. Before we move to the lecture, it is time to remind you again for 14th Asian Aerosol Conference, which will be taking place between 1 to 4 December in Mumbai. Please visit conference website for more details, submit your papers, and do come to Mumbai. Now coming back to today's lecture, the lecture focuses on results obtained from research performed at high altitude laboratory of IITM at Mahabaleshwar. To tell you more about the speaker, I now invite Dr. Padma, who is also from IITM Pune and also our executive committee member. Dr. Padma, please.
Thank you, Dr. Manish. A very good evening to all. So it's my pleasure to introduce our today's distinguished speaker, Dr. G. Pandithurai, Scientist G and Project Director at Indian Institute of Tropical Meteorology, Pune. Dr. Pandithurai began his research career at IITM and earned his PhD from the University of Pune in 1998. He later pursued postdoctoral research at the University of Maryland, USA, and also served as a visiting professor at the Center for Remote Sensing, Chiba University in Japan. With over 30 years of dedicated service at IITM, Dr. Pandithurai has held various prominent positions and currently leads as Project Director of Atmospheric Research Testbeds. And among his many achievements, he established the High Altitude Cloud Physics Laboratory, well known as HSCPL at Mahabaleshwar, and India's first short-range urban weather radar network in Mumbai, and Atmospheric Research Testbed, now popularly known as ARTS, in central India near Bhopal. He's a renowned scientist in the field of aerosol cloud precipitation interactions, radar remote sensing, and atmospheric radiation, and published over 175 peer-reviewed research papers and mentored around 12 PhD scholars, making a significant contribution to the scientific community. And his outstanding contributions have earned him numerous awards, including IITM's Golden Jubilee Award, and twice he received Silver Jubilee Award for his outstanding research. And he also received Certificate of Merit from the Ministry of Earth Sciences for excellence in atmospheric science and technology. So with this brief introduction, I now welcome Dr. Pandithurai to deliver his lecture.
Thank you, Dr. Padma.
Thank you.
Also, thank you, Dr. Manish and Dr. Neeraj and all IASTA executive committee members. Also, I want to thank today, I could see my research supervisor and mentor, Dr. Devara. He's also here. Thank you very much for all of you. And I thank IASTA for giving me an opportunity to talk to you on this aerosol effects on clouds and precipitation. So my title is Aerosol Indirect Effects. First of all, I want to acknowledge all my colleagues who contributed to this research program and also PhD students. So whatever I'm presenting is mainly the results of my PhD students and colleagues at High Altitude Cloud Physics Laboratory. So with this, I'll begin my talk, and the outline of my talk is next slide. Yeah. So I'll give a brief background and why these aerosol indirect effects are important in the current climate change scenario, and what are the IITM's initiatives for better understanding on aerosol cloud interactions. And I'll give some highlights of the recent results. Last 10 years, we have been working on this. More than 10 years, we have been working on these projects, and there are several process understanding studies, and some of them I'll highlight, which are how the aerosols and CCN, which are cloud condensation nuclei, and CDNC is here, cloud droplet number concentration relationships, and what is the role of aerosol size and hygroscopicity on CCN activation process, and how one can estimate aerosol indirect effect if you have collocated measurements of aerosols and cloud microphysics, and also the ice nucleating particles, which are also very important to understand the cold clouds. So we have some measurements on that, and we utilize the measurements to develop a parameterization so that it could be implemented in numerical models. So with this, I will summarize my talk, and this is the schematic. You can see that this the aerosols, it has a direct effect through scattering and absorption. It can influence the top of the atmosphere radiation balance, and in turn, it can affect the climate directly. Whereas the cloud active aerosols, CCN and IN, ice nucleating particles, so they can modify the cloud microphysical structure and precipitation. In turn, it can modify the general circulation of the atmosphere and global hydrological cycle. So we have this is a very complex subject. So as compared to direct radiative effects of aerosols, the indirect effects are still not very well understood. Next slide, please. So now coming to the process understanding, I just want to explain how the aerosols are indirectly affecting the climate system. The first indirect effect is the cloud albedo effect. Here, if you have more number of aerosols, there will be more cloud droplet number. For a given liquid water content, if there are more cloud droplets, then the droplet sizes will be smaller. In turn, it can enhance the reflectivity of the cloud, so which we call albedo effect. Next slide, please. So here you can see a cloud with more number of smaller droplets can have more reflective surface area than a cloud of the same volume with fewer larger droplets. So you can see for the same volume, if there are more cloud droplets, it can increase the reflective surface area of the cloud by acting as cloud condensation nuclei. This is well-known effect called cloud albedo effect or Tommy effect. Next slide, please. So this is one example for cloud albedo effect. These are ship tracks. So how the emissions from ship can enhance the reflectivity. So if you look at from satellite, you will see the ship tracks, how it enhances the reflectivity of the cloud. So next, please. So the second aerosol indirect effect is the cloud lifetime effect. Here, if we have more number of smaller droplets, so in turn, it will delay the warm rain initiation because of suppression of collision coalescence efficiency. So I'll show you pictorially in the next slide. So you can see left-hand side, you see the large droplets which can collide with the falling raindrop. Whereas if there are droplets are very small, it can follow the streamlines, airflow streamlines, and bypass the falling drop, so that it is limited collision coalescence efficiency. So in turn, it will delay the warm rain initiation. Next slide, please. So here is a review paper by Jivan Fan on aerosol cloud interactions. So here they have presented what are different mechanisms, significance, and challenges. So if you look at the left-hand side, you see the clean cloud, and right-hand side, you see the clouds in the polluted environment. So the mechanisms which describes the impact of aerosols on the whole life cycle of deep convective clouds. So if you look at the polluted environment, the convective cores detrain the large amount of cloud hydrometeors, so which leads to larger expansion, and the cloud gets dissipates very slowly. So in turn, you can see the polluted clouds have large cloud cover and a higher cloud top height and thicker clouds as compared to the clouds in the deep convective clouds in the clean region. Next slide, please. So what you are seeing here is how these aerosols, for example, primary and secondary particles, and how if you have the optical properties of aerosols, like aerosol optical thickness, single scattering albedo, asymmetry parameter, we will be able to estimate the effective radiative forcing due to aerosol radiation interactions. So what you're seeing here, ERF suffix ARI is the effective radiative forcing due to aerosol radiation interactions, whereas the below you see the cloud activity, which the cloud active aerosols such as cloud condensation nuclei, ice nuclei, it can alter the cloud microphysics, and the radiative forcing due to aerosol cloud interactions depends on how well we understood the cloud condensation nuclei activation processes or ice nucleation activation processes. Next slide, please. So this is the IPCC reports wherein you can see our understanding on radiative forcing due to greenhouse gases are far better as compared to the aerosol effects, especially the aerosol cloud interactions. So you can see there is a red box wherein purple color is shown, that is aerosol cloud interactions. So you can see the large uncertainty in the aerosol cloud interactions. So we have next slide, please. Because of this large uncertainty, our Ministry of Earth Sciences and IITM, Indian Institute of Tropical Meteorology, initiated projects for better understanding on aerosol cloud precipitation interactions. One such project is CAIPEX, which is Cloud Aerosol Interactions and Precipitation Enhancement Experiment. Under this project, this was implemented somewhere in 2019, I guess 2019 or sorry, 2009. So in this project, instrumented aircraft is used to observe aerosols below the cloud basis and cloud properties by penetrating into the clouds with the instrumented aircraft at different heights of the cloud. So with aircraft, we have an advantage. We can go close to cloud base, and also we can enter into clouds at various levels so that we can profile cloud microphysics and its vertical structure. At the same time, the aircraft has limitations that you cannot carry a lot of complex instrumentation, and also the sorties are limited for few hours. So you cannot understand the diurnal variation, or you cannot understand the detailed chemistry, and because you cannot carry high-end heavy equipments like mass spectrometer, etc. But now that there are miniature equipments have started coming. Next, alternatively, we set up a high altitude cloud physics laboratory at Mahabaleshwar. That's a second project. Anyway, I'll just, in the CAIPEX, the more details you can see from the BAMS paper from Dr. Tara Prabhakaran, so which describes the project objectives, which are aerosol cloud precipitation interactions. And also the additional objective is to formulate a scientific basis for rain enhancement. Next slide, please. So here, you can see the vertical profiles. As I said, aircrafts can penetrate clouds at various levels. So these are vertical profiles of cloud droplet size distribution. The left-hand side, you see a cloud in a polluted environment. Also, you see different lines. So they are sampled at different heights. So the black line, if you see the legend, which is the last 4 digits, shows 4546, means it is 4.5 kilometer. So the profiling was done from 4.5 kilometer to 7.5 kilometer. And what you can notice is the cloud drop size distribution did not broaden much. So in the plot, you are seeing a center line, red line, so which is a threshold droplet diameter, about 24 micrometer. To initiate collision coalescence, the drops have to reach to this minimum size of about 24 micrometer. Whereas another sample you see at the right-hand side, which is taken in a coastal location, Mangalore. The left-hand side observations are conducted in the northern part of India, Pathankot, whereas the right-hand side, this is collected over a marine environment, Mangalore. So here you can see the profiles are taken from 800 meters to 3.4 kilometer. And also you see the broadening of cloud drop size distribution. So it shows that the collision coalescence effect will be started because it exceeded the 24 micrometer diameter. So we can see the warm rain initiation, whereas in a polluted environment, the warm rain initiation got suppressed. However, there could be the vertical development of clouds can be observed, and you can see sometimes thunderstorm or cold rain process will be dominant. Next slide, please. So in the same case, the aircraft also observed images, the cloud droplet images. You can see large ice crystals are observed from 6 kilometer to 7.5 kilometer. Because so we have a lot of dust aerosols over this region during pre-monsoon, which act as a efficient ice nuclei, and it can nucleation can take place even at lower temperature, like minus 14 degrees Celsius. Next slide, please. So this is another study from the KIPEX project that you can notice that if there is a more pollution, rain will form at a higher elevation. This is a study from Mahen Konbar. So it's showing that how the polluted regions, the warm rain initiation can start at a higher elevation. And there are some modeling study by Gayatri showing if you increase the cloud condensation nuclei, so which will alter the freezing level, and the precipitation formation can get delayed. Next slide, please. So with this background, so what we need to improve our understanding on aerosol cloud interactions. So first we should understand better how these aerosol cloud condensation nuclei and ice nuclei activation processes can be better represented, how these physical and chemical characteristics of aerosols can control the activation of aerosol to CCN, and what type of aerosols can serve as ice nucleating particles. So with this objective, we set up a high altitude cloud physics laboratory at Mahabaleshwar in the Western Ghats of Maharashtra. It's about 100 kilometers from Pune. So the altitude is about 1400 meter above mean sea level. Next slide, please. So this shows the Western Ghats elevation, what you see in the left-hand side. So the color represents the elevation, and so it starts from even Tamil Nadu, Kerala up to what I have shown is up to Maharashtra. Advantage is that during monsoon, at higher altitude regions, clouds float very close to surface. I think those who are from other parts of India, like Munnar, those who are from Kochi, you must have seen in Munnar, all the warm clouds float very close to surface, and it can interact with the aerosols which are emitted from surface or transported from other parts. So we can observe the aerosol cloud interactions and try to understand how it modifies the rain forming processes. Okay, so the right hand side you can see that there is a high precipitation, which is a precipitation climatology. What you see is the high precipitation over Western Ghats. So because of orographic influence. So our objective of this laboratory is to gather long-term observations so that it will enable us the best test bed to study aerosol cloud precipitation interactions and also the orographic convection and precipitation processes. So under this, in this laboratory, we have a suite of measurements, instruments for observing aerosols and cloud active aerosols like CCN and ice nuclei. And for clouds, we have cloud probes and cloud radar, etc. We had deployed. Then for precipitation, we have different types of disdrometers to get a raindrop size distribution, rain intensity, and also the vertical profiles using radars. In addition, we also have VOC measurements because Western Ghats is highly vegetated region, so it can contribute to secondary organic aerosols. The VOCs can get oxidized and contribute to secondary organic aerosols, and in turn, it will play a major role on CCN activation process. Next slide, please. Yeah, these are some pictures of the suite of instruments which are deployed in a high altitude cloud physics laboratory. So first one, what you are seeing is the cloud combination probe, and there are other instruments also. If you happen to visit Pune, you can visit the laboratory. And last year we organized a instrumentation workshop, and all the participants were taken to the laboratory for operation and how the instruments are working and how the data processing is done. Yeah, next slide, please. So if you look at this plot, the right-hand side, you see the aerosol, how it varies with the time, diurnal variation of aerosols in different seasons. The top panel shows for monsoon, and the middle one is for winter, and the bottom panel is for a pre-monsoon season. So the left-hand side, you are seeing the cloud condensation nuclei measured using a chamber cloud condensation nuclei counter at different supersaturations. So overall, if you see the aerosols and CCN, the variation looks similar, right? So, and there are some seasonal changes. For example, in monsoon, you have high aerosols during morning hours and low aerosols in the evening hours. Whereas in pre-monsoon, it's a reverse trend. Morning it's low and the evening it is high. And in winter, you have a similar type of peaks in the morning and afternoon. So CCN also has similar variation, and higher the supersaturation. If you increase the supersaturation, more number of aerosols can get activated as a cloud condensation nuclei. Yeah, next slide, please. So to understand this CCN activation process, this CCN activation depends on the following factors. First is the particle size, dry diameter, and the chemical composition, which tells about the mixing state and chemical composition, and also hygroscopicity. What is the water uptake of these particles? For example, for ice nuclei activation, it majorly depends on the temperature and the aerosol type and concentration. Next slide, please. So again, for when you talk about hygroscopicity, it is the ability of water uptake by aerosol particles. See, generally, if the humidity is high, the particles can get swell, right? So it can modify the size and refractive index of aerosols. In turn, it can impact the visibility and direct radiative forcing. So the other thing is it's highly related to the hygroscopicity is highly related to the activation of aerosol into CCN. So in turn, it will impact cloud and precipitation microphysics. So, and the atmospheric aerosol contains significant quantity of organics, and the mixture of different chemical species makes it more complex to represent its hygroscopicity. Next slide, please. So we had an experimental setup for um, measuring the hygroscopicity. So by measuring the growth factor of aerosols. So what you see in the atmosphere, we have a polydispersed aerosols. Ambient aerosols are polydispersed, and these particles will be dried to low relative humidity, for example, up to 30% RH. Then you use a differential mobility analyzer to size select the particles. So you only select a certain size of the particles. Now from polydispersed, you are having a monodispersed aerosols at a selected size. Then you measure how many number of particles are there. Then you send the particles to next DMA and CPC, wherein you have a humidification chamber. You increase the humidity to 80 to 90%. And what will happen is that because of high humidity, the particle will grow to larger size. If you take the ratio of the size now and the dry size, you will get the growth factor. The growth factor can be directly measured. Then we can estimate hygroscopicity of the particle, which is commonly called as a kappa. And also you can look at how many particles got activated as a CCN through CCN counter. Okay, you know how many particles entered into CCN counter and how many got activated in as a CCN. So you can directly get the activation fraction. Let us say if I send 100 particles and all 100 got activated as a CCN, then the activation fraction is 1. I send 100 particles and 50 particles got activated, activation fraction is 0.5. This is how you know the activation fraction. Next slide, please. So through growth factor, we try to look at how this hygroscopicity or kappa varies with the size. Okay, so you can see that in the lower size range, up to 100 nanometer, there is a decrease in hygroscopicity with the increase in particle size, whereas after 100 meter, which is we call accumulation size regime, so you see an increase in hygroscopicity with the increase in size. So you see a different phenomena. It is a one of my PhD student, Abhishek Ray, he has done these experiments. Next slide is part of his PhD thesis, and he tried to look at how this hygroscopicity varies and what is its relationship with the chemical composition. So the chemical composition, what we have shown in the bottom, is through aerosol mass spectrometer. So it can give you the non-refractory particles below 1 micrometer. So he tried to look at seasonally how the chemical composition of aerosols in winter and pre-monsoon and how it's related with the hygroscopicity. So you can see in pre-monsoon, you have a higher hygroscopicity, even though the organics are slightly more. But the main reason for higher hygroscopicity is the chlorides are almost 50% higher and ammonia also slightly higher. So which leads to the chlorides have very high hygroscopicity. You can see that some typical K values are given here. So there are ammonium chloride has like 1.02 hygroscopicity as compared to organics, which is 0.1. So next slide, please. So we try to see how the aerosol hygroscopicity and CCN activation fraction varies with the time for different size of particles. So what you notice is the green color is activation activation fraction. The line is the hygroscopicity derived from HTDMA, which is hygroscopic tandem differential mobility analyzer. So you can see almost a similar variation. You see that higher the kappa, you have higher activation fraction. Next slide, please. Here, if you look at for different supersaturations and for different hygroscopicity and what is the activation fraction for a different supersaturation. So you see look at the highlighted red color box. So you go from 50 nanometer. It's for a 50 nanometer particle, but we are increasing the supersaturation from 0.1% to 0.9%. You can see higher the supersaturation, higher the activation fraction, right, for higher hygroscopicity. So if you look at column wise, it's for a given supersaturation, you are looking at for different size of the particles. So we try to see how the CCN activation fraction depends on the kappa values, hygroscopicity, and the supersaturation. Next slide, please. Now I'm coming to the aerosol indirect effect estimates. So there are some equations you are seeing at the slide. So for example, ACI suffix n, which means aerosol cloud interactions estimated through number. The other one, the second one, 1b, equation 1b shows ACI suffix r, which is derived from cloud effective radius. Okay, so the denominator is alpha, which is a proxy for aerosol concentration. And the numerator is the cloud microphysics. Either it could be droplet number or droplet radius or cloud optical depth, anything you can take. So relative changes in cloud microphysics with respect to changes in aerosol levels. So what you see in the figure is that you are seeing aerosol concentration. They all are independent measurements. So aerosol concentration is derived from one instrument and cloud condensation nuclei is derived from another instrument. And you observe the cloud droplet number concentration using a probe. I will show you how the cloud probe measures the cloud microphysics. So if you look at three independent measurements co-located, higher the aerosols, you have higher cloud condensation nuclei and higher cloud droplet number concentration, right? So at the same time, the bottom panel shows you the effective diameter, cloud droplet effective diameter. When the cloud droplet number concentration increases, the cloud droplet effective diameter tend to decrease. So this is what we call as a aerosol first indirect effect. So we can estimate through these relative changes. Okay, the next slide. So here, this is one snapshot, like how the aerosol concentration and the cloud droplet number concentration varies when you observe at different times. So this is some snapshot of that. Next slide, please. So this is how the clouds are measured from ground. So generally, these probes are also can be used in aircraft so that you fly into the cloud because you are in a moving platform. Here you are in a stationary location and clouds are coming, clouds are near surface. So you draw the cloud air mass into your instrument. You are seeing two probes here, which are optical probes, which are laser based. Through optical scattering, you can get the cloud drop size distribution from 3 to 4 micrometer up to 200 250 micrometer by combining these two probes. So the right hand side, what you're saying is one probe which can measure up to 30 micrometer or 50 micrometer, whereas the other probe can go up to 200 250 micrometer. Yes, next slide, please. So these are some of the research papers came out from this project, that how the aerosol indirect effects can be estimated using ground-based measurements. So here also you can notice that higher the cloud droplet number and higher the cloud condensation nuclei, you can see there is a reduction in cloud droplet size, so which is used to derive the aerosol indirect effect. Next slide, please. But as I said, through both the methods, you can see there is a discrepancy between indirect effect estimated from size, cloud droplet size, and cloud droplet number concentration. The green circles are derived through cloud droplet size, and the black spheres are through number. So you can see there is a systematic difference between these both these estimates. So what we notice is that aerosols not only increases the CCN concentration and cloud drop distribution, so it also changes the relative dispersion of cloud drop size distribution. So relative dispersion means, it can alter the drop size spectrum. The width of the spectrum can get narrow, or the mean radius can go further low. So the dispersion is nothing but the ratio between the spectrum width to the mean radius. So if you can apply this dispersion effect into the aerosol indirect effect estimated from the number concentration, then the both matches very well. So if somebody uses droplet number concentration, then it is better to use the offset which comes from the dispersion effect. Next slide, please. So now I'll move to slightly another topic, which is ice nucleation measurements. So you have seen that CCN, which is cloud condensation nuclei, the activation fraction can be up to 0.5 or 50% or 60%, whereas ice nucleating particle is a very small subset of atmospheric aerosol. It helps in the formation of ice particles. Its concentration is very less compared to CCN, say, which is 1 in a million of aerosol particles. So the old studies uses offline sampling and analysis. Here we used a continuous flow diffusion chamber, which we call spectrometer for ice nuclei, for online measurements of ice nucleating particle in an air sample. Next slide, please. So there are potential sources of INP. You can see the mineral dust from deserts and aerosols of biogenic origin from oceans, and the bioaerosols and organic aerosols from the forests, and soot aerosols from industry and biomass burning. So they all can be potential sources of ice nucleating particle. Next slide, please. So there are several mechanisms to form ice. So I don't want to get into details because there are several mechanisms, like through heterogeneous nucleation modes. Next slide, please. So early method is to use a cloud chamber where the air sample is cooled by sudden expansion to create supersaturation. Then they started using the samples on membrane filters. So these filters are exposed to freezing temperatures and supersaturation inside the diffusion chamber to identify the ice nucleating particle. Recently, the CFDCs, which are widely used for online measurements of ice nucleating particle. Next slide. So this is a spin chamber we used, spectrometer for ice nuclei. So we conducted experiments from minus 25 degrees Celsius to minus 35. Try to see how the ice nuclei varies. So we also have some images, like these are some salts and sulfates. Yeah, next slide, please. Then we try to look at how it seasonally varies these ice nucleation particle number concentration. You can see they are very less, like tens of particles per liter. But there is a temperature dependence you can see. As if you go to lower temperatures, you can activate more number of ice nucleating particles can get activated. Next slide. So we try to see that what are all the existing parameterization schemes are there, what people reported from outside, and how our measurements are comparing with the previous measurements with in other parts of the world. So we try to look at the parameterization, which is mainly depends on the course number, aerosol number concentration, and temperature. So the old parameterizations mainly depends only on the temperature, not depends on aerosols. So here this depends both temperature and the aerosol number concentration. So the existing DMARC scheme is not, if you as such you use, so it's not fitting very well with the measurements. So we try to change the parameterization here. Next step. Yeah, there were, you can see how these ice nucleating particles vary at different temperatures. For example, if you look at the green portion, which are the lower higher temperatures, you can say higher temperatures, -5 to -15. The green particles are mainly kind of bioaerosols, so which can get activated even at lower temperatures. And the orange is yellow and orange are dust aerosols. Green is mainly biological particles, and the red is like biomass burning. So mainly if you look at biological and rural aerosols, and the dark blue, which is marine aerosols, can get means efficient ice nuclei even at the higher temperatures like -10 or -15. Next slide. So what we can see is there are, this schematic gives you the aerosol cloud precipitation related processes occurring within a typical GCM general circulation model grid box. So if you look at the low level clouds, wherein the aerosol activation, scavenging by droplet coalescence, all these processes are taking place. And whereas in the ice clouds, the cirrus clouds have ice nucleation and ice formation and precipitation initiation. So all the some are like primary processes and some are secondary processes. So there is a complex interaction between aerosol effects on clouds and precipitation. So we need more studies on these topics to reduce the uncertainty which is currently prevailing in the aerosol cloud interactions. Next slide, please. So with this, I'll summarize that aerosols are a necessary ingredient for cloud droplet formation and ice nucleation processes. However, they can modify cloud microphysics to generate feedbacks that may amplify or dampen their influence. CCN activation process studies are being made using size-resolved aerosol chemistry and hygroscopicity. So we also developed aerosol-dependent ice nuclei parameterization for Indian region and tested in numerical models, which I have not shown. Some of the simulations were done with regional model and even with direct numerical simulation models, which is not part of this talk. So observations are essential for process studies. and its parameterization representative to different climatic regimes. Next slide. So with this, I'll summarize. And there is a short video you can watch later on the cloud physics laboratory in the Western Ghats. So the picture shows how the rain shaft is being observed by a radar in Western Ghats. So with this, I think I'll stop my presentation and take up some questions. Thank you.
Okay, thank you. Thank you so much, Professor Pandithurai. It was really very interesting and very informative talk. I'm sure there will be many questions. So what I request audience to please raise your hand, and I will ask you to ask, interact directly with the speaker. In case if you have any problem, you can type a question in the chat box and I will read out for you. Okay, so I can see the first hand, Dr. Kalapura Reddy. Yeah, please go ahead.
Pandit sir, thank you very much for the enlightened talk.
Thank you, Madhu.
Sir, it was very interesting, but I'm sorry that I joined at something I couldn't able to follow. But the one interesting picture which I have shown is the diagonal cycle of maybe it is a CCN or supersaturation. It shows around 18 hours is the minimum value. 18 hours is a local time, right, sir?
Yeah, all are local.
That green. So that is the not time that we can see more precipitation?
No. I don't know which figure you are referring to.
It's
but
a green color you have given in a 3 panels and it's a diagonal.
Okay. That is, I think, CCN and aerosol variability.
Right, sir.
What I tried to explain is that how the aerosol and CCN is varying.
Okay.
And the CCN also showed similar variability. However, different diurnal patterns are seen in different seasons. So, for example, in monsoon, you have a higher number concentration in the morning hours.
Yes, sir.
And in pre-monsoon, you have higher CCN in the afternoon hours. It's mainly because of sources and boundary layer evolution, I guess. And there are sources are dominant in different seasons differently.
Yeah, sir. Actually, what I'm going to try is that these are the surface observations over the maybe our high altitude cloud physics laboratory.
Yeah,
so,
right.
can it be taken as a general with the height or general with any other place? Can we buy this? Can these variations? Can we expect the same thing?
Anyway, so it's there will be regional variability.
Yes,
Yeah, similar variations were shown even in the Pune also in with the aerosol optical depth measurements, but not in monsoon. So we cannot do optical measurements during monsoon.
Yes, understood, sir.
Yeah, but there are diurnal asymmetries in different seasons.
Yeah, sir. Why I am asking this one is I just want to take this such observations may be happening at monsoon core zone also.
Dr. Reddy means let us have the pointed question so that other people also can interact.
Right, sir. That is what. So we would like we have the cloud radar observations. Can we take like you are telling ice nucleation so at that cirrus level? Can match this one? Just I want to ask it is expertise. I just want to ask Pandit sir.
Yeah, ice nucleus. See what way the chamber will measure at ground, but
Yes.
radar can see it even at
Particular height, sir.
yeah.
So can we make a attempt on it? That's what I would like to ask. It is a surface that is at 14
Yeah,
kilometers.
you can see. Anyway, there is a variability with the surface to exponentially or with some scale height of weights. So we can extrapolate it. Yes.
Excellent. Thank you very much, sir.
Thank you.
Okay,
I have
thank
some
you.
other question I can ask
Yeah.
you.
Yeah. Thank you. Yeah, anyone else? Until somebody else raises hand, let me read out some questions which are there in the chat box. So Somnath, he has asked CCN activities depends upon chemical composition. Any idea about the chemical, physical, or chemical property or anion? Or means he's asking whether what type of chemical composition is affecting.
Yeah. Actually, I have shown you that
Yeah, kappa value you have shown for
Yeah.
different composition. Yeah.
how the
Yeah.
chemistry varies. For example, we have shown with the two different seasons how this chemical composition alters the hygroscopicity parameter. So, which in turn will change the CCN activation process.
And another question was written by Dr. Kalapurati. Is diagonal cycle minima around 18 hours IST with CCN by SS?
I
Or
think
does that
yes.
specific to a location or in general?
We cannot generalize that everywhere it will happen similar, because it depends on the sources prevails in the specific regions. So my intention to show that is not that when it is minima or when it is high. So what I want to show is how what fraction of aerosols can get activated as a CCN, and why different seasons have different peaks. What are the different activities or sources? So for one such explanation, we were thinking in monsoon why it is, even though periodically washout mechanisms are there, still we are having a higher aerosol number concentration. So it's we were thinking that it could be due to secondary organic aerosols coming from the volatile organic compounds oxidation. These are all some speculations. So we are still working on VOCs, which is mainly, I think, high in pre-monsoon because it varies on temperature, the VOCs are.
Let me add one question here. Means when you were talking about the chemical composition, the kappa value for organics you have shown 0.1. But organics in themselves are highly variable. You know, there are 1,000 type of organic compounds.
Yeah, this is only theoretically people use for organics 0.1. Then they use some mixing rules. Okay, but even we cannot consider organics have 0.1. So different organics, the oxidized organic aerosols higher kappa. So that is I shown typical values for organics.
So okay, average value is taken as 0.1, but it can be highly variable depending on the composition of organics.
Just I have shown, I have not used that organics values because we are not using the ZSR mixing rules to compute kappa. We are computing kappa or deriving kappa through growth factor. But if somebody uses only without growth factor, one uses chemical composition, then they have to use mixing rules, ZSR mixing rules, and they have to derive kappa. In our case, earlier we did that. Now we have growth factor measurements. We can derive kappa from growth factor.
Another hand raised. Harshvardhan, please go ahead.
Yeah, nice presentation, sir. Sir, I want to ask about the that you discussed the threshold diameter for the initiation of collision and coalescence for the warm rain process. But somewhere I read about that cloud effective radius of precipitation threshold is range between 12 micron to 14 micron. So I'm a bit confused about this threshold diameter, how we choose actually.
Okay, I think the 12 to 14 may be the radius.
Okay, I got it. And this one is the diameter.
People use radius, diameter. So that's what 12 is equivalent to 24 micrometer.
Yeah, got it. Thank you.
Okay. Another question written by Akash from IAST. He is asking why is it not necessary to constrain the CDNC-CCN relationship at a fixed LWC while estimating ACL?
Yeah, to estimate aerosol indirect effect, we have to consider for a given liquid water content. I have shown you that aerosol indirect effect estimates were made at multiple different liquid water content bins. So we have to use for a fixed liquid water content only, we can do this.
And the other question is by Arya. And the question is, how is supersaturation created and varied?
Okay, in CCN, the chamber walls, the temperature gradients are adjusted such a way that the center of the chamber, the supersaturation will be calibrated with that. So the temperature gradient between the walls, it's a diffusion principle. So supersaturation is created with the temperature gradient.
Let me add one more question from my side.
Yeah.
Very simple question. So what is the basic difference between CCN and INP? Means you said that INP are very limited. CCN, we know that means they are huge.
Okay.
So what is the basic difference?
Yeah. See, for ice nucleation, for homogeneous ice nucleation, it cannot happen. So generally, either CCN activation, everything is heterogeneous, right? So for homogeneous activation, it takes a very high supersaturation. But ice nuclei, but see, there are plenty of aerosols can act as cloud condensation nuclei, but very few will act as a ice nuclei.
So what property decide that they can act
The
as
property is either it should have biological material or some minerals. So they are efficient ice nuclei because of their morphological structures.
Okay. Another question by again Akash. So during simulation measurement of CDNC and aerosol concentration, how can we account for correction due to interstitial aerosol particles, that is, particles that have already activated and gone beyond the size range of standard aerosol instruments?
Yeah, I think for that there are methods people use CVA inlets so that they can avoid this problem. So we are also planning to add in future the counter virtual flow inlets, CVI impactor inlets, so that we can avoid this interference between already activated aerosols.
Another question by Hari Krishna Devi Setti. Question is, under warming condition, is there a possibility that aerosols may evaporate before they can activate as cloud condensation nuclei and form cloud droplets? If so, how can this issue be addressed?
Aerosol will not evaporate because it's a material. Maybe some vapor form it can get evaporate. Once it's a particle, it will not evaporate. But cloud droplet, the water can get evaporate, and it can put back the aerosols. See, every droplet will have a nuclei which is aerosol. If cloud goes off, cloud evaporates, it will leave the particles. So, but not the aerosol will not evaporate unless it's very vapor form or organics.
Can I?
Yeah,
Can
yeah,
I
please,
interact
please,
on?
sir. Please, sir. Yeah.
Okay. Dr. Pandithurai, it is an excellent presentation,
Thank you.
and the topic chosen is also an excellent one. So it is a highly complex topic, but of course you made it as simple as possible. I really appreciate and all the whatever experience you gained. I just wanted to ask 2, 3 clarifications. I don't want to call them as questions, as clarification. You have shown a suite of equipment at Mahabaleshwar, one slide. Could you get or observe any event where all our maximum facilities have been used to pursue that event? Because so variety of things I have seen. Any opportunity you got where maximum number of equipment have been used to study a particular phenomenon or particular event or episodic. There's one thing, of course, if you right now don't have probably for me, you please
I'll answer
mail
that.
me.
Yes, I'll answer.
And the another thing is, one question, one of your piece of information I could not digest fully. All along you are talking about aerosol, which are of hygroscopic. You are telling aerosol number is high, means cloud condensation also goes up, and then cloud activity also will be more positive and all. But of course, the other part of aerosol, the absorbing type, hydrophobic type. So when hydrophobic type enters into the picture of your aerosol ensemble, how actually the aerosol cloud interaction, precipitation or aerosol cloud radiation, this chain will turn its shape.
Yes, sir. Actually, see, for CCN activation, only we are talking about the hygroscopicity. For ice nuclei, not required because the mineral dust is of hydrophobic, but still it can play a role in the ice nucleation process. So for CCN activity, so hygroscopic aerosols are favorable, but still, even the non-hygroscopic particles with the aging, it can get an external coating. So, which also will lead to activating, because it's not that the core only will be absorbing type, but the shell, outer shell, could be of material which are of hygroscopic. So that will also play a role in CCN activity. The other question about our suite of instruments are grouped into aerosol, cloud, precipitation. So our idea is to see how aerosols influence cloud microphysics, or how it in turn modify the precipitation process. So we, for different processes, we use different things. For example, nucleation mechanisms. So you have to go further below 2 micrometer using a air ion spectrometer. So, and for secondary organic aerosols, so we use PTRMS, and it's not necessarily for any objective, all have to be used. But for different processes, different suite of equipments are used. So, but co-located multiple observing facilities can support better scientific understanding. That is the idea.
Really, I'm very much excited. But at the end, with all your know-how, experience of so many decades of working on aerosol in the aerosol field, what is your concrete message to the aerosol community, particularly those who are struggling to better understand the aerosol cloud precipitation interaction? Because when I was doing, I used to I used to think that refractive index plays a lot of role in understanding this relationship. In your case, variety of instruments you have, and then variety of sophisticated things have come out. And then, could you, what the message you give it to aerosol cloud interaction people?
Yeah, still I
To
think
understand better what else we require. Our
okay.
present wealth of instrumentation is sufficient, but only thing is we have to work a lot. What is your opinion?
Yeah, I think we will never say everything is there. See,
No, no, just
for example, we have spectrometers, mass spectrometers. Right now, we are able to only observe the non-refractive material. So we are unable to see the refractive materials yet. So I think there are techniques are going to maybe evolving that will be able to close complete chemistry. Because right now we are only talking about the non-refractory composition. Even for uh, closure studies, still there are some gaps are there.
So still I remember your frequent usage when we both were working closure experiments.
Yes. Yeah.
Can you?
Correct. We were trying to see how we can predict CCN, because ultimately the modeling communities need a simpler form of CCN representation. So if you have aerosols, and if you have size and some basic chemistry, how do we better predict the CCN or ice nuclei? So that's what even though we need complex measurements, but ultimate end product should be like simpler representation, so that it could be easily implemented in numerical models. So
of course, the model and then observation should go hand in hand, no doubt about it.
yeah.
So anyway, I'm very happy, very happy by listening to you such an extempo topic. Nice,
Okay,
nice.
okay, thank
My
you,
special
sir.
thanks to you,
Yeah,
Dr.
thank you,
Pandit.
sir. So
I
Vijay,
have a
Vijay,
question.
yeah, Vijay, please. Vijay,
Yeah, thanks, Neeraj.
Anil afterwards.
Hello, sir.
Hello.
Yeah.
Hello.
Excellent talk. It's always pleasure to listen to you. I have a very quick question. I have seen one of the slides you mainly showed the derivation of kappa values. I don't quite remember for different sizes, selective sizes. Usually kappa value will increase with increasing size. which basically reflect there is a change in composition. But I don't remember clearly, but what I saw was the composition, the kappa value was same for all the sizes.
I think we are. So I showed size dependent hygroscopicity, right? So
Correct.
I
Yeah.
shown in the icon mode up to 100 nanometer, there is a decreasing trend in kappa. Then above 100 nanometer, everybody has reported that increase in size, increase in kappa.
Yes.
So that's what I think previous studies have shown. What we notice is below 100 nanometer, there is a reverse trend. So the icon mode, we have a reverse trend, which we found from our measurements. And also the other graph, what I've shown is the diurnal variation of kappa and activation fraction, how it is varying. So almost, I think it was going hand in hand. That's all.
Okay. Thank you.
Okay, thank you. Anil?
Yes, so hi, I am Anil Patel from Ahmedabad University, and I just want to know one thing about the supersaturation that is required for the particle to go under activation, because you need like more than 0.01% of supersaturation to get the activation or nucleation for the fog or cloud to form, right? But there are some evidences in the literature where they found that the activation or nucleation can still occur when the RH is less than 100%. Did you find any such event from any polluted environment?
No, we have not found anything, because even in the chamber experiments, you don't get anything get activated even below 0.05 or something. So we don't see anything, because it has to condense, right? So it has to condense. I have not seen below 0.01 supersaturation any particle got activated. So, I'm not sure. Yeah.
No.
Okay. Anyone else? In chat box, people are still keep writing questions. Okay, so let me read just one or two more and then we will stop. So Kamran Ansari is a student from PRL. He's asking, are there any plans to measure the aerosol semi-direct effect?
Kamran, I think, right now we don't have any methods to directly observe evidence for the semi-direct effect or quantitatively measure semi-direct effect. So as of now, we don't have any plans.
And Akash, who asked the question earlier, he's continuing the question probably. Sir, I seek further clarification. Could you please clarify why the CER-CCM relationship is defined at fixed LWC, but not the CTNC-CCM relationship?
Yeah, because cloud effective radius will change with the increase in liquid water content. Because if you don't fix that, then you don't know whether it is the change is due to CCN or change is due to LWC. So that is a problem with when you use size.
Okay, anyone else? Otherwise, we will move to the last part of the talk. Okay, it seems not. So let us move to the last part of the talk. So that is vote of thanks. So it is indeed my great pleasure to give vote of thanks. And first of all, I would like to thank Dr. Pandithurai for accepting my request. I just want to inform all the audience that first thing is this person, you have seen him continuously, and you will not believe that he is almost 60 years. After 2 days, he is going to retire. And whomsoever means people know that people are very busy before they return because they have to wind up multiple things. But still, I requested, I insisted, and he kindly agreed. So thank you so much for accepting our request.
Welcome.
And then I would like to thank our BRC team who always do the things behind the scene of this lecture series. And most importantly, I would like to thank all the audiences. It is because of you we are continuing this series, and you will keep coming, and we will keep bringing new and different speaker on different topics so that you can learn. And for your information, after the talk, this whatever talk is there, it will be available on our IASTA YouTube channel. So you can follow all our social media platform. We will be getting updates on what are things happening, and all these kind of talks will be available there. So with this, I would like to thank you all again. And that's it. Thank you.
Thank you, sir.
Thank you, Dr. Neeraj and Manish, Dr. Manish, and all BAS team for arranging this. Thank you.
Thank
Okay.
you, Dr. Pan.